So the next topic we're going to do is called molecular orbital theory. And we need to develop this theory because there are certain bonds that valence bond model could not predict. So just like we did with valence bond model, the molecular orbitals will hold 2 electrons and they have definite energy. So we will be mixing orbitals from single atoms to generate what we call a molecular orbital. So I'll post the video for this on my site as well. So the first example we're going to look at is a hydrogen and a dihelium molecule. In order to generate a molecular orbital, we have to overlap 2 atomic orbitals. And for hydrogen, we have 2 1s orbitals that will overlap to make the molecular orbital that we call the sigma 1s orbital. It can hold 2 electrons. So if we draw a picture of it, each hydrogen is represented by a red or a blue arrow. When we mix together to make a molecular orbital, we generate a sigma 1s and a sigma star 1s molecular orbital. For a hydrogen molecule, only 2 electrons exist, so they will both be in the sigma 1s orbital. So what happens if we try to make a dihelium? So now there's going to be 2 electrons from each element, and there'll be a total of 4 electrons that need to occupy the sigma star and sigma 1s orbitals. The bond will become unlikely because both the sigma and the sigma star orbitals are occupied. So if we draw a picture of that, we'll have a total of 4 electrons that need to go into the molecular orbital. 2 electrons in the sigma 1s and 2 electrons in the sigma star 1s. So once we fill the sigma 1s and the sigma star 1s, we're going to fill the sigma 2s and sigma star 2s orbitals. Then when we get to the p orbitals, there are 3 degenerate p orbitals that need to be mixed together with 3 other p orbitals for a total of 6 molecular orbitals. We'll be able to put 12 electrons in these 6 molecular orbitals. But the order that they will fill from lower energy to higher energy will be dependent on where they are on the periodic table. So for example, this shows the order of the pi 2p as being lower than the sigma 2p orbitals. So there's a total of 4 electrons that can fit in the pi 2p orbitals, 2 electrons in the sigma 2p, 4 more electrons in the pi star 2p, and 2 electrons in the sigma star 2p. The other way to order them is the sigma 2p is lower than the pi 2p. The upper sigma star and pi star antibonding orbitals stay in the same order as the previous example. So when we go to fill the sigma and the pi orbitals in these molecular orbitals, it'll depend on where we are on the periodic table. So for example, if we do diboron, dicarbon, or nitrogen gas, the order will be different than oxygen, fluorine, and neon gas. So if we have the diboron, the dicarbon, or the nitrogen gas example, we would tally up the total number of electrons for the entire molecule and start filling in the molecular orbitals from lowest energy to higher energy. So this example shows the order that we would fill for oxygen. So we would fill the sigma 2p before we would fill the pi 2p. So say, for example, we were going to do the molecular orbital for oxygen gas. We would find the total number of electrons, which in this case will be 16. And then we are going to fill the orbitals from the lowest energy up. So we have 16 electrons that need to be filled in, and we'll fill in the pi, the sigma star, the sigma 2p, the pi 2p, and eventually the pi star 2p orbitals. We notice that there are 2 unpaired electrons in the pi star 2p orbital. And this is one of the reasons why there needed to be a rearrangement of the order of these two, the sigma 2p and the pi 2p, because oxygen is paramagnetic experimentally. So when you want to calculate the bond order, you calculate the total number of bonding electrons minus the number of antibonding electrons and divide by 2. So if you have a bond order of 0, that means there is no bond and the molecule would not exist. But if a bond order was 1, you would have a single bond. Bond order of 2 would be double. Bond order of 3 would be triple. And doing the oxygen with the sigma 2p lower than the pi 2p shows us that oxygen is paramagnetic. So if you have to do the bond order for O2, you should say the bond order is 2. So which statement is true about the molecular orbitals that result from mixing 2 atomic orbitals with the same energy? You're going to get 2 molecular orbitals, one with a lower energy and one with a higher one. So for example, we would label them sigma 1s and sigma star 1s. So when we go to do the hybrid orbitals for double bonds, we need to remember that we need to have one of the electrons must be in a hybrid orbital and one in an unhybridized orbital. So for example, if we look at carbon in carbon dioxide. So here's our Lewis structure for carbon dioxide. So we need to make sure that carbon is making 2 double bonds. So that means 2 electrons must be in the hybridized orbital and 2 of them must be in the unhybridized orbital. So if we were going to draw, we would have carbon and it's got 4 electrons, so we're going to draw 4 degenerate orbitals and we're going to fill in our electrons. And since we need an unhybridized and a hybridized for each of the double bonds, we're going to draw our hybridization lines over 2 of them. And the label for this orbital would be an sp orbital. And so this electron and this electron could be used for the double bond, and that one could be used for the other double bond. So we would say that that carbon dioxide has sp hybrid orbitals, which is exactly what we would expect because we know that sp hybrid orbitals have the linear molecular geometry. So when we have singles and double bonds, there's different types of electron density between the 2 atoms. So a single bond, we give the name sigma. And the pi bonds were given the name pi. And it's a double bond that contains 1 sigma and 1 pi bond. When we go to look at the pictures, we'll see them on the next slide. Triple bonds have 1 sigma and 2 pi orbitals. So in order to illustrate what a single bond looks like, this is what a sigma bond would look like. So there's a sigma between these 2 chlorines, and a double bond has a sigma in between this carbon and this oxygen, but it also has a pi bond, which is this red, kind of like hot dog shaped orbital. And this bond density right here and down here are all part of the same sigma bond. So a sigma bond has two lobes, a red lobe up above and a red lobe down below. So there is a double bond between this carbon and this oxygen. So if you were going to tally up the number of sigmas and pi's in this molecule, you would say 1, 2, 3 sigmas and 1 pi. Now if we have a triple bond, we're going to have 1 sigma and 2 pi orbitals. And when we overlap these 2 pi orbitals, they end up looking like the parts of the fins of a fan. So these are considered 2 pi orbitals and 1 sigma orbital in between. So when we go to tally up the number of sigmas and pi's in the molecule, we need to make sure that we know what this structure looks like. So if we need to draw what this is, remember this is going to be a 6-membered ring. And one way to draw it is to draw it with alternating double bonds. And so it's easier to draw it this way so that you can tally up the number of sigmas and the number of pi bonds. So when you do that, you're going to have hydrogens coming off of each corner to give us our C6H6 structure. So then we should have 12 sigmas and 3 pi's. So when we draw our nitrate ion, we should be able to see we've got 3 sigmas and 1 pi bond. So single bond there, and a sigma and a pi for that double bond. And then C2H2 is going to look, the Lewis structure will look like that. So that's a sigma, and there's 1 sigma in there. So that's 3 sigmas, and a triple bond has 2 pi bonds. So when we have electrons that are spread out over the entire molecule, we label them as delocalized. Quite often, they are localized, which means that the electron density stays between 2 atoms, like these 2 carbon atoms with this double bond. Typically, delocalized electrons have a lot of resonance structures that can be drawn, and so we've done several examples of delocalized electrons using the example of benzene.